All right, welcome back to Math TV with Professor V. In this video, we're going to cover Chapter 8, Confidence Intervals for one population mean. If you aren't subscribed yet, please do so now. It would really mean so much to me to help support this channel, and give this video a thumbs up. All right, so first we're going to talk about estimating a population mean and confidence intervals for one population mean when sigma is known. So now we're shifting gears and we're beginning our discussion of the second branch of statistics, which is called inferential statistics. And inferential statistics includes generalizing from samples to populations, performing estimation and hypothesis tests, and determining relationships among variables and making predictions. So some terms to know. In statistics, estimation refers to the process of estimating the value of a parameter from sample information. Okay, so remember, parameters are values that describe a population. Statistics come from a sample. So we're using basically information from a sample, a statistic, to estimate the value of a parameter, because typically it's impossible to get all of the data from a population. So let's look at some examples. Consider the statement, today, U.S. coffee drinkers consume approximately 3.1 cups per day on average, with the cup size being 9 ounces. Oh my. So here's the source. And notice, every member of the population is not surveyed, right, in this statement, in this study. Instead, the mean that they're reporting here of 3.1 cups per day is an estimate based on a sample. So under what conditions should we consider this a good estimate? Good meaning it is actually representative of what the population mean, mu, truly is. So now let's talk about different types of estimates. First one, which is what we just looked at, is a point estimate. So a point estimate is a specific numerical value that estimates a parameter. Sample measures, statistics, are used to estimate population measures, parameters. And it's easy to remember, samples go with statistics, S and S, and then population, P, goes with parameters. So here's an example. I want to estimate the average age of students at Harvard University. So what I do is I sample only 150 students who attend Harvard, and I find that X bar, the average age of students in this sample, is 21.4 years. We say that X bar is the best point estimate, meaning it's just a single value, point estimate of mu, the actual population mean. X bar is called an estimator. And there's 3 properties that make an estimator a good one. The first one is that it's unbiased. When we talk about bias in statistics, it's different than maybe how you're used to hearing bias used in other aspects of life. When we say something's not biased statistically, that means that the expected value of the estimate of these estimates is equal to the parameter being estimated. Expected value equals parameter value. Consistent. Consistent means that as the sample size n increases, the value of the estimator approaches the true value of the parameter. So your error, your sampling error, should decrease as n increases. That makes it consistent. And relatively efficient means of all the statistics that could be used to estimate the parameter, the relatively efficient estimator has the smallest variance. Okay, again, not using the term efficient maybe in the way you think, ooh, that was done so quickly, so swiftly. No, when we talk about efficiency in statistics, we mean smallest variance. All right. So if we're referring to the example above, would it be accurate to conclude that the average age of all Harvard University students is 21.4 years? Well, no, not necessarily. what might be problematic about using a point estimate in this way? Well, first of all, we don't know how the sample was collected. Assuming it's a simple random sample though, and we did our best effort, right? When we're collecting candidates for the sample, there always is sampling error and the possibility that the sample isn't representative of the population. You know, 21.4 may be very close to mu, but because we don't have a census, right? We didn't take the age of everybody at Harvard. That would mean we have a census. Because we don't have a census, we can't guarantee that X bar is equal to mu. There's just no way. So what does that mean? Well, generally, statisticians prefer the following over a point estimate. So instead of just giving one single value, what statisticians prefer is using an interval estimate, and that's what we're going to study in this chapter. So an interval estimate is an interval or range of values that are used to estimate a parameter. And the interval, I mean, it may or may not contain the value of the parameter being estimated, but instead of just saying, for example, 21.4 years, then you would say maybe it's between 21 and 22 years or something. So we'll talk about how to make these intervals, okay? But the idea is instead of just giving a single value, you give a range of values. Each interval estimate has an associated confidence level. So this is important because that helps you construct it. The confidence level is the probability that the interval estimate will contain the true parameter value, assuming that a large number of samples are selected and that the estimation process is repeated. So common choices are 90, 95, and 99%. So you'll say the confidence level is set at 95%, and therefore 95% of the confidence intervals that are constructed will contain the true parameter mu. 5% of them won't though. Join the interval and the specified confidence level to get a confidence interval. And that's a specific interval estimate of a parameter calculated using sample data and the specific confidence level of the estimate. Okay, and we're going to get more into how changing the confidence level affects the confidence interval, but this should make sense to you. If you're upping the confidence level, your confidence interval has to get wider because you're basically guaranteeing more often that your intervals will contain mu. So you'll never have a confidence level of 100% because then your confidence interval would be all real numbers, which is not insightful or not helpful. Okay, so the highest confidence level that we typically work with is 99%. Now here's the idea of how to construct them. Okay, so by the central limit theorem, we'll abbreviate it, given a normally distributed variable or a fixed sample size n greater than or equal to 30, the distribution of the sample means is normal. This is what we studied in the last chapter. Recall that mu sub x bar is equal to mu and sigma sub x bar is equal to sigma over root n. Now, if we repeated the estimation of a population mean a large number of times, over and over and over, okay, 95% of the sample means, these estimates, would fall within plus or minus 1.96 standard deviations of the mean. And the range of values, this range of values is called the confidence interval. So think back, remember when we talked about the normal distribution and finding z-scores and probabilities? We did that in StatCrunch. And then we also went backwards with StatCrunch, right? And we could say, oh, if I know I want 95% of the data here in the middle of my normal distribution, we were able to go backwards and figure out what the corresponding z values would be under the normal distribution. And it turns out for 95%, it's positive 1.96 and negative 1.96. Remember, the standard normal distribution is symmetric. So if you're splitting 95% of the data in the middle, then those two z values should match up. and that also means you have 0.025, 0.025, or 2.5% on each of the tails, okay? What does that mean? For us, that means that within 1.96 standard deviations of the mean, which is at 0, we have 95% of the data, okay? And so this is a value that's going to come up a lot. 95% goes with plus or minus 1.96 for our z values, okay? Finally, what you can say is 95% of these 95% confidence intervals will contain the actual value of the population mean mu. So mu is somewhere in here 95% of the time that we're making these confidence intervals. And so the way you would construct it is you would take x bar, your sample mean, subtract 1.96 times sigma over root n. That would give you your lower bound for your confidence interval. And then mu's in between there somewhere, and then x bar plus 1.96 times sigma over root n. That would give you your upper bound. All right? And then if I changed this percentage from 95 to 99, then we would use a different z value down here, and that would affect these values here, making the interval larger. Okay, we'll talk about that in a minute. Oh no, I spoiled it. Okay, so if the confidence level increases, will the confidence interval be wider or narrower? Well, like I just said, if we changed it to 0.99, right, and now you want 99% of the data to lie within this interval, you have less on the edges, and these values are going to be more extreme, right, than 1.96. So this is going to be a wider confidence interval. So here's the formula for finding a confidence interval of the mean given alpha. What is alpha? Well, the confidence level, let's add this in here, the confidence level equals 1 minus alpha. So basically alpha is also 1 minus the confidence level. So that means if your confidence level is 90%, okay, that means alpha would equal 1 minus 0.90, which is 0.10. And that means 10% of the data, right, is not within that interval. So you would have 5% on each of the tails. And that goes with the score. We write z sub alpha over 2 because 5% is in each of those tails, the left and the right, and that equals 1.65. And then 95% confidence level has a z sub alpha over 2 of 1.96, which we saw earlier. And 99% has z sub alpha over 2 equal to 2.58. You don't have to memorize these because we're going to use StatCrunch for most of it. But if you just want to keep these three handy, they come up so often, it's not a bad idea. I had memorized them not on purpose, but just by doing enough practice problems, okay, over the years. So here's the formula for the confidence interval of the mean given alpha. You construct it with x minus z sub alpha over 2 times sigma over root n. And then that's less than mu, which is less than x bar plus z sub alpha over 2 times sigma over root n. So the only thing that changes depending on the confidence level is that value for z sub alpha over 2. And you can see as the confidence level gets bigger, these values of z sub alpha over 2 also get bigger, don't they? Okay, good. So assumptions when we're making a z confidence interval is that the data collected was using a simple random sample. You weren't just sampling your BFFs, okay? We also had a normal population or a large sample, and the clincher is that sigma, the population standard deviation, is known. Now think about this. This is a little weird. I mean, how in the world are you going to have the population standard deviation and you're trying to make a confidence interval for the population mean because you don't know it? that's not really realistic, you know. So theoretically, we're gonna make different kinds of confidence intervals, not based on the normal distribution, but this is the foundation for moving forward. Okay, good. All right, some more terminology. Hang in there. I know it's a little bit dense with the, the concepts and the theory, but once we get into some examples, they won't be so bad. So the maximum error of the estimate, E, is the maximum likely difference between the point estimate of a parameter and the true value of the parameter. The maximum error of the estimate is also sometimes referred to as the margin of error. So E is equal to Z sub alpha over 2 times sigma over root n. And you might notice that's exactly this expression here and here. That's our error. So another way that you'll see confidence intervals represented is that you just write x bar plus or minus E, because that's going to be x bar plus or minus Z sub alpha over 2 times sigma over root n. So basically we say, here's our sample mean x bar. Mu is somewhere in here, I don't know where, 90, 95, 99% of the time. Okay, you set the confidence level. And the maximum error, or the maximum amount that you're off by using x bar, is equal to E in either direction. Okay? Good, so let's try some examples. I think you'll feel better once you see how they're constructed, and then we will hop into StatCrunch in just a minute. So example 1A, a random sample of 54-year-olds attending daycare centers provided a yearly tuition average of $3,987 and a population standard deviation of $630. That is an excellent price, my goodness. Okay, find the 95% confidence interval of the true mean yearly tuition and summarize the results. All right, so here let's list what they gave us. We have 54-year-olds, so n is equal to 50. That's my sample size. This yearly tuition here is a sample average, okay, because it came from the 54-year-old. So x bar is 3,987. And then notice they told me we have the population standard deviation of 630. So that's a sigma, not an S. That's a big clue that we're supposed to use this, make a Z confidence interval. Okay, later we're going to be making T confidence intervals. So watch out. And then they told me we're making a 95% confidence interval. So that means Z sub alpha over 2 is equal to 1.96. Okay. So I think the easiest way to set it up, remember, to make your confidence interval, you have x bar plus or minus E. What's E? The maximum error of the estimate, or the margin of error. So we're going to have x bar plus or minus, remember the formula for E was Z sub alpha over 2 times sigma over root n. So in this case, Z sub alpha over 2 is 1.96 times sigma over root n. And then now I'm going to substitute everything in. So x bar was 3,987 plus or minus, I have 1.96 times 630 over square root of 50. Okay, and then it's appropriate if you want to get your calculator out now. So I have 3,987 plus or minus this error, margin of error comes out to 174.63. And I'm going to take 3,987, subtract 174.63. That's going to give me 3,812. That's the lower bound for my confidence interval. And then 3,987 plus 174.63 is 4,162. So here's my confidence interval. That's all there was to it. Okay, so I did some of it in the calculator, so I'll just write it out here. This is 3,987 minus 174.63, and then this is 3987 plus 174.63. Got it? I don't need to see all the steps to get there. So let's summarize what we just found. One can be 95% confident that the population mean yearly daycare tuition is between $3,812 and $4,162 based on a sample of 50 4-year-olds. I'm sure they actually sampled whoever was paying the tuition. I doubt the 4-year-olds were aware and not the direct participants in the survey, but whatever. Okay, what is the amount of error for the estimate? Round to the nearest tenth. So we actually already have it. Remember, this right here is E, my error. So that means 174.63 is my error, but they want me to only round to the nearest tenth. So that would be 174.6. Okay. Very good. How are you feeling? See, it's not so frightening. It's not so frightening. We'll do a couple more. A U.S. travel data center survey reported that Americans stayed an average of 7.5 nights when they went on vacation. Sad but true. I mean, we don't get the kind of vacation here that Europeans get. All right, the sample size was 1,500. Assume the population standard deviation was 0.8 nights. Okay, find the 98% confidence interval of the population mean and summarize. Let's go through, list what everything is. Average of 7.5 nights, so that's my X bar. The sample size was 1,500, that's N. And population standard deviation is 0.8 nights, so that's sigma. And then in A, they're asking for a 90% confidence interval, so Z sub alpha over 2 for 90% is 1.65. I listed that earlier. It's good to know what those are when you're doing these by hand, but like I said, you don't have to memorize them because when you do them in StatCrunch, it's going to just plop in the Z sub alpha over 2 value for you. But you know, you want to know what's going on behind the scenes, not just be a mindless peon. You want to know, why are these confidence intervals getting larger, right? When alpha is changing. Okay, I digress. So we have X bar plus or minus, it's Z sub alpha over 2 times sigma over root n. Yes? Yes. So this is going to be 7.5 plus or minus 1.65 times 0.8 over rad 1,500. And in the calculator, this all comes out to about 0.034. So 7.5 minus 0.034, I'm going to have 7.47, and then 7.5 plus 0.034, just round to 2 decimal places, 7.53. In the homework, they will tell you how many decimal places to round to. I just felt like doing one more than the data that was given to me, than the mean. Okay. Maybe I should have done one extra in the last problem. Whatever. Okay. So summarize, one can be 90% confident that the population mean number of vacation nights for Americans is between 7.47 and 7.53 nights based on a sample of 1,500 Americans. Okay, same thing. Now they're asking us to find the 99% confidence interval. So 99%, changing the confidence level just changes Z sub alpha over 2. For 99%, it's 2.58. Those again come from our standard normal distribution. Okay, so now we're going to have X bar plus or minus 2.58 times 0.8 over rad 1,500. Nothing else changes. And then X bar was 7.5 plus or minus. This max error ends up being 0.053. So 7.5 minus 0.053 is 7.45. And then 7.5 plus 0.053 rounded to 2 decimal places, 7.55. Ooh, come on, make a cute little box, please. Yes. So one can be 99% confident that the population mean number of vacation nights for Americans is between 7.47. Oh no. I wrote down the wrong one. 7.45, excuse me. 7.45 and 7.55 nights based on a sample of 1,500 Americans. Okay, which interval is wider and why? I don't even need to look back at them. I know it's going to be the second one, the 99% one, because the confidence level increased, which means z sub alpha over 2 increased, which means error increased, which means wider interval. And it makes sense. If you're going to increase your confidence that the true parameter mu is in that interval, you got to make it wider, right? To guarantee that you're going to find it in there. And look, we can tell. This one went from 7.47 to 7.53. Okay, if you need to see it on a number line, here we go. So the mean was 7.5, right? First interval goes down to 7.47, 7.53. This was our 90% confidence interval. And then the 99 went down to 7.45 and up to 7.55. That's why it was at 99%. Okay? So with increasing the confidence level comes a wider interval. So that's why we don't always go for the highest confidence level, because sometimes you don't want so much error, right? This is error. This is potential error. So upping confidence level means you're increasing your maximum error. So there's a payoff, you know, maybe you don't want so much error, so you're going to lower the confidence level. It just depends on context. It really depends on what you're using this confidence interval for. Okay, so I've been promising you StatCrunch. Let's get into that so you can see how to make these confidence intervals for your homework. All right, here we'll look at this question number 14. It says, according to a study of political prisoners, the mean duration of imprisonment for 39 prisoners with chronic post-traumatic stress disorder was 32.4 months. Assuming that sigma equals 41 months, so remember, that's population standard deviation, determine a 95% confidence interval for the mean duration of imprisonment mu of all political prisoners with chronic PTSD. Interpret your answer in words. So what you're going to do is go down to Get More Help and open up StatCrunch. They give you links to the standard normal table. We don't need that. So hop into StatCrunch, and then this time they just gave us the summary, meaning they gave us the mean, they gave us the size of the sample, they gave us sigma. So you don't have any data to import. You just go stats, z stats, one sample, and then with summary, not with data. And here, let's see, they gave us the sample mean. It was 32.4 months. The standard deviation they gave us was 41, and the sample size was 39. Default, it's set to do a hypothesis test. We don't want that right now. We'll do that in the coming up. So we want confidence interval for mu. Check the confidence level. They did want a 95% confidence interval, which is what it says here. So that's perfect. And then compute. That's all you need to do. So here they give you the lower limit for the confidence interval and the upper limit. And then this is also the standard error. All right, so they're going to ask you now to enter the lower limit and upper limit for the confidence interval, and we're just rounding to one decimal place. So here we go, 19.53, that'll just round to 19.5. And the upper limit is going to be 45.3. Okay. Interpret the confidence interval, select the correct choice below, and fill in the answer boxes to complete your choice. So there is a 95% chance that the mean duration of imprisonment of all political prisoners will equal the mean of the interval. No, it doesn't mean that the means are the same. Remember, the confidence interval, the real mean could be anywhere within that. So I'm not liking the sound of A. Let's read B. We can be 95% confident that the mean duration of imprisonment, mu, of all political prisoners with chronic PTSD, is somewhere between, and then I'm just going to re-enter what we have here, 19.5 months and 45.3 months. Fantastic. Okay, I did want to look at another question that had a little bit more going on to it. Let me redo it. Okay, so a random sample of 20 maximum sentences for murder yielded the data in months presented to the right. Use the technology of your choice to complete parts A through D below. So first they ask us to find a 90% confidence interval for the mean maximum sentence of all murders. And this is important right here. They said assume a population standard deviation of 25 months. We need to enter that. Otherwise, we will not get the correct result. So this time you're going to actually go here, take that data, click open in StatCrunch. Here we go. And pretty similar process. So you're going to go stat, z stats, one sample. And this time it's with data, right? We have all the data values from the sample. So that's what you're going to select. We're using the data that was in variable 1. Enter the standard deviation, otherwise you will not get the right answer. So they told me standard deviation was 25 months. And no, not a hypothesis test. We want a confidence interval at 90%. So let's compute this. Okay, again, they want us to round to 1 decimal place. So lower limit is 282.05. We'll round up to 1. And then the upper limit, 300.44, is going to stay. Excellent. Thank you. Now they want us to obtain several graphs. Don't worry, you're not going to do this by hand. So they want a normal probability plot, box plot, histogram, and stem and leaf diagram. Okay, so normal probability plot, in case you forgot. Here's all our data sitting tight in column 1. So you go you go graph, QQ plot. Select variable 1, and then we want normal quantiles on the y-axis, and click compute. So it looks something like that. The only one that looks remotely close is D. So that one's pretty obvious. Then they also want us to create a box plot with the data. Okay, no problem. So graph, go down to box plot, variable 1, and I think that should be good. Do I need to do anything else? Compute. Oh, theirs is turned. Doesn't matter. Just imagine rotating it in your head. The key thing is there's one outlier on the right. So that's going to be B. Just turn it in your head, okay? Good. And then the last graph is histogram. All right. So they may not make the classes the same way as it is right here, but we'll just do our best. So graph, histogram. And let's compute. It's not matching up perfectly because, ours here, notice we have, I think we broke up the classes a little differently. They probably took the outlier out. Because here's 260 and ours is at 250. So kind of only looking at this portion, then I would say it's D if you don't go as low. Oh no, that wasn't right. Okay. Then if I'm going to take another guess, I'll guess A. Okay, good. So the only reason that they weren't matching up, you guys don't have a meltdown, is because they grouped their classes differently than what StatCrunch gave us. And it's, guess wrong maybe or whatever. Move on. And then we need a stem and leaf. So for stem and leaf, notice they have 2 digits in the stem, 1 digit in the leaf. So if I want mine to match up, I do need to tell them that the leaf unit is 1. And that should be enough. So let's see. Which one matches up? It looks like A, right? 366. That's what I'm looking at. The 67. Yeah, it's A. Check. Nice work. Okay, remove the outliers from the data and then repeat part A. So they want us to do the confidence interval again and remove the outlier. And remember, we did have an outlier. I think it's 376. This little guy over here. So just come back to the data. I don't need that. Where's the outlier? 376. I think I passed it. Oh, here it is. Just clear it out of there. Okay, and then we're going to repeat everything. So stat, z-stats, 1 sample with data, variable 1. Don't forget to give them the standard deviation. I forgot what it was. Hold on. 25. Okay. 25. And is it still, 90% confidence interval. And compute. All right. Did it change much? Not really, huh? 200. Let me scroll down so you could see. This is going to be 277.4 to 296.2. Check. So let's compare. After we took out the outlier, 277 to 296, originally 282 to 300. I mean, a little bit tighter, but not a whole lot of difference. So comment on the advisability of using the z-interval procedure on these data. So A says, although the data do not contain outliers, oh, that's not true. It did have an outlier. So forget A. Stop reading immediately. That one's wrong. B, although removal of the outlier does not appreciably affect the confidence interval, okay, keep talking. Using the z-interval procedure here is not advisable because the sample size is moderate. That's true. The data contain an outlier and removing the outlier is not justified. Yeah, I mean, it was a small sample. Maybe we needed more and that poor little outlier should be there. Who knows? B is sounding good. Let's keep reading the rest. C, since the data do not contain any outliers, well, that's not true. I know it's not C. Don't even read the rest of that. D, since the removal of the outlier does not appreciably affect the confidence interval and because the sample size is moderate, it is advisable to use the z-interval procedure. That's the exact opposite of B. So really you have to determine which one is the correct case. The sample size was moderate. N was only 19 and really 30 is kind of like our cutoff. So I would say let's use B. Okay, for smaller sample sizes, as you're going to learn in the next chapter, it's better to use the t distribution. Okay, so 30, you want to think of like at least 30 or more, then it's okay to use the z sometimes. Okay, let's check. Yay, so that's it. Next topic in our discussion is sample size. So the size of the sample needed to make an accurate estimate depends on the amount of error that you're willing to tolerate and the confidence level. So remember our error is equal to z sub alpha over 2 times sigma over root n. What I want you guys to do is solve for n, isolate n. Okay, so to get n by itself, I'm going to start off by just dividing both sides by z sub alpha over 2 so I can get rid of it. So now I have e over z sub alpha over 2 equals sigma over root n. I can take the reciprocal of both sides of the equation. It's still going to be equal. So this means z sub alpha over 2 over e. See, I flipped the left-hand side. That's going to equal rad n over sigma. And I'm happy because I'm trying to get n by itself. I want it in the numerator. Now I can multiply both sides by sigma. So what I have is z sub alpha over 2 times sigma over E equals rad n. And then to get n by itself, all I need to do now is square both sides, right? So I can write my final result as n equals z sub alpha over 2 times sigma over E squared. Okay, very good. And this gives us the formula for the minimum sample size needed for an interval estimate of the population mean. And in practice, this is something that statisticians and researchers do all the time. They will actually set how much error they are willing to tolerate in their study first. They're going to decide how much error they're okay with. And then from there, they'll go backwards and figure out, okay, well then how big of a sample do I need? Okay. And notice, since n represents a minimum sample size required for a specified amount of error, then we'll always round the value of n up to the nearest whole number. So even if n comes out to be like 7.1, you would make n equal to 8 when collecting your data, because you can't round down to 7. They have an inverse relationship, n and error. So as n goes up, error goes down. And if n goes down, error goes up, and vice versa. So if you have any little decimal remnant, you gotta bump up n to the next whole number. All right? Let's look at an example. A researcher is interested in estimating the average salary, oh, how sad, of teachers in a large urban school district. If she wants to be 95% confident that her estimate is correct and the population standard deviation is 1,050, how large a sample is needed to be accurate within $200? Okay, so here's my formula to compute n, right? That's what we're trying to figure out. And she wants to be 95% confident. Well, what does that mean for us? That means z sub alpha over 2 is equal to 1.96. This is the population standard deviation, so sigma is 1,050, and she wants to be accurate within $200. So basically she's saying, I'm okay with an error of $200. That's the most error she wants to have. Okay, so then we're going to say n is equal to z sub alpha over 2 times sigma over E squared. Z sub alpha over 2, that was 1.96. Times 1,050, divide this by 200, and then square the whole thing. Okay, again, this is fine. You can use your calculator right now. And you should get 105.88 or so, which we always will round up to 106. And like I said, even if this was 105.01, again, you would round it to 106. You can't round it down to 105. Taking a smaller n means more error. We gave you the maximum tolerated error, which is 200. Okay? Good. So remember that if you're ever designing a study, you can set n depending on how much error you're willing to tolerate. Okay. Now, I mentioned earlier, it's not really reasonable to come up with a confidence interval for the population mean, and then somehow you magically have the population standard deviation. Like, who gave you that? The statistics fairy or what? So if you don't have sigma, if you don't have the population standard deviation, you can still make a confidence interval. It's just not going to be a z interval, okay? So when the population standard deviation sigma is known, the confidence interval for the mean is computed using the normal distribution. We know this, but in most cases, sigma is unknown. So we estimate it using the sample standard deviation S. And when we're using S as an estimator for sigma, especially when the sample size is small, then we use values from the t-distribution, not the normal distribution, to construct confidence intervals. And when n is smaller, the critical values of the t-distribution are larger then the corresponding values of the z distribution. So basically, we're going to have, instead of z sub alpha over 2, t sub alpha over 2, and those values are usually bigger. So you can't be as precise or have as tight or narrow of an interval without sigma. So that's why we switch to the t distribution. And usually, if you're going to use the t distribution when sigma is unknown, we require that the population is normally or approximately normally distributed, or n is greater than or equal to 30. Really, every stats textbook kind of changes up the criteria when to use the z, when to use the t. For our purposes, just base it on if you have sigma or s, And the samples still have to come from simple random samples. Okay, so let's look at some characteristics of the t distribution. Ways in which the t distribution is similar to the standard normal distribution. It's bell-shaped, okay? It's still symmetric about the mean. The mean, median, and mode are equal to 0, so this is all the same as the normal. And they're located at the center, and the curve never intersects the x-axis. So these are all similarities between t distribution and normal distribution. Ways in which the t distribution differs from the standard normal. First thing is that the variance is actually greater than 1, which makes it more spread out than the standard normal distribution. And then the t distribution is a family of curves based on the concept of degrees of freedom, which is related to sample size. So sample size is n, right? That's n. And that determines what the degrees of freedom are for the t distribution. So you'll have, here's one t distribution, here's another one, here's another one. This looks terrible, so don't look, okay. But we'll look at a picture in a minute. And then the last difference is, as the sample size n increases, the t distribution actually approaches the shape of the standard normal distribution. So what the heck are these degrees of freedom that I mentioned? Well, they're the number of values that are free to vary after a sample statistic has been computed. So when we're constructing a t-confidence interval for the mean, we will use df, which stands for degrees of freedom, is equal to n minus 1, sample size minus 1. And you might be thinking, what in the world does that mean? Why is it n minus 1? Well, here's the reason. If you have 10 numbers, okay, and I tell you the mean of those 10 numbers is 80, but I don't tell you what the 10 numbers are, you can make them up to be whatever you want, not all 10 of them. You can freely assign the first 9 values to be whatever you want, but after you've selected that 9th value, the 10th value is fixed. You don't have any wiggle room after picking the first 9 if you want to guarantee that x bar is 80. So that's why we say that the degrees of freedom are equal to 9, because you can assign those first 9 to be whatever you want. That's all the freedom you have in assigning those values. So it's always 1 less than the sample size. Okay, for this case, when we're talking about making a t-confidence interval for the mean. Okay? So here's the formula for the confidence interval of the mean given alpha. Remember, alpha is your 1 minus the confidence level. And it looks pretty identical to the formula when we made a confidence interval based on the normal. It's just now we have t sub alpha over 2. And instead of sigma, we have s. Okay? So those go together. Again, degrees of freedom, n minus 1, and we use a t-confidence interval when sigma is unknown. Okay, that's going to be the standard protocol in this class. So error E, instead of z sub alpha over 2, it's t sub alpha over 2 times s over root n. And again, you could write your confidence interval as x bar plus or minus E. Good? Okay. So one mean t-interval procedure, the purpose is to find a confidence interval for a population mean mu. And we have to assume simple random sample, normal population, and sigma is unknown. So where do we get the values for t sub alpha over 2? Remember, I gave you the values for z sub alpha over 2 based on common choices of alpha. I gave you the 3. Well, for T, there's so many more because you have to take into account degrees of freedom. There's only one standard normal, and N can be anything. But if N changes for the T distribution, then that changes the degrees of freedom, which changes the value of T sub alpha over 2. So, oh my goodness, when I used to teach statistics a long time ago, back in the day when I first started, I would give my students a table. So you would look up, like, if the degrees of freedom was 13, that means your sample size was 14. And we set alpha to be 0.1, then alpha over 2 would be 0.05. You'd have to do all this thinking and then come find your value, right, for T sub alpha over 2. You're not going to use a table, and it's impossible to memorize them all, right? Because there's so many based on the confidence level and then the sample size. No, you can't memorize these. So we're just I'm not going to give you a table. You're just going to use StatCrunch to get through all these exercises, okay? So I'll show you right now how to do it, but I do want you to know the values when you're doing your homework online, they pop up magically and beautifully, but there's so much that goes on behind the scenes, okay? So let's hop into StatCrunch so you guys can see an example with these T confidence intervals. All right, now let's look at an example where we're going to make a T confidence interval. The example reads, suppose that the average time spent per day with digital media several years ago was 3 hours and 19 minutes. For last year, a random sample of 20 adults in a certain region spent the number of hours per day with digital media given in the accompanying table. Preliminary data analyses indicate that the T-interval procedure can be reasonably applied. Find and interpret a 99% confidence interval for last year's mean time spent per day with digital media by adults of the region. And they gave us right here the sample mean, X bar, and sample standard deviation, S. So I don't really need to click here and open the data because I have all the summary stats that I need. So I'm just going to go to get more help so I can open up StatCrunch. And they're asking for a 99% confidence interval. And I'm just going to click Stat, T-stats, one sample with summary. And the sample mean X bar was 5.65. The sample standard deviation S was 2.23. And the sample size, they told me in the beginning of the problem that there were 20 adults, 20. And we want a confidence interval. The level, they want a 99% confidence level, and let's compute. So lower limit is here, upper limit is here, and they're asking us to round to 2 decimal places. So lower limit will be 4.22, and the upper limit will be 7.08. Yes, because 0.76, that will round up. Well done. Okay. Interpret the 99% confidence interval, select all that apply. A, with 99% confidence, the mean amount of time spent per day on digital media last year by all adults in the region is between the intervals bounds. That sounds correct to me. Let's read the rest just to be sure, but I'm going to select that one for now. B, there is a 99% chance that the mean amount of time spent per day on digital media last year by all adults in the region is between the intervals bounds. So this is very similar to A. It's just that they use the word chance instead of confidence. So that's what makes it incorrect. It's not the correct interpretation of how we set up confidence intervals. Let's read C. 99% of all adults in the region spent, no. So the confidence level doesn't tell you what proportion of the population falls within that interval. So no, that's not going to be correct. And then 99% of all possible random samples of 20 adults in the region have mean amounts of time spent per day on digital media last year that are between the intervals bounds. So that's not quite exactly on point. A is still sounding the best. They did say select all that apply, but the others just have something a little bit off about them. It's a word here or there. So let's just check. Okay, we're good. Let's move on to the next one. Let's redo it. So here it says researchers compared 14,613 annotated genes from one species with their orthologs in another species to identify genes. This is like a useless sentence. So if it if it stresses you out when they get too wordy, just don't read them. A simple random sample of 14 tissue types yielded the numbers of genes shown in the accompanying table. Use technology to decide whether applying the t-interval procedure to obtain a confidence interval for the population mean appears reasonable. Explain your answer. So here's the data of all of the number of genes. I'm going to open it in StatCrunch. And really, what we need to do is determine the normality of this sample, of the data here, because we only have a sample of size 14, which is very, very small. And so whether or not we can apply the t-test is based on whether or not this distribution is approximately normal. So what we're going to do is go to graph. We can do a QQ plot. That's one option. Variable 1, and let's put the normal quantiles on the y-axis and see what this looks like. So everything's kind of clustered about here. It looks sort of normal, but then we've got these 2 outliers down at the bottom. So that's making me nervous. I'm thinking it's probably not a good idea to apply a t-interval procedure because this sample is so small and it doesn't look like it's a normally distributed sample. So let's see if we can fill in all these blanks here. Applying the t-interval procedure to obtain a confidence interval for the population mean, I'm going to say, does not appear reasonable. It is required that the population standard deviation sigma, well, remember, sigma is unknown when you use the t-distribution, and this condition is satisfied. That's true. We don't have sigma. But let's keep going. The sample is not or is? I mean, I would say it is random because they told me they made a simple random sample. I'm not going to assume they're lying for any reason. But because of the sample size, it's only 14, it is required that the population can be reasonably assumed to be normal. That's what we need in order to apply the t-interval procedure for such a tiny sample size. A normal probability plot indicates that there, one low outlier, one high, no. At least one low outlier, yes. No, that's not true. There are outliers at one, no. So here, at least one low outlier, but no high outliers. And it is not reasonable to assume the population is normal. Nice work. Okay, so that one might be a little bit tricky, but every iteration I've done of this problem, they all fall into the same pattern. So hopefully you guys will be good.